Okay, so okay, so today is our last lecture in this introduction, say, to trees. I don't know if I have time at the end. I will tell you something about priority queues. Okay, so today I'm telling you about chapter 12 in Introduction to Algorithms book. And by the way, just as a reminder, I mean, the things that I said yesterday about linear programming are in chapter, I think, 29 or something in the same book. Okay, so linear programming is one of the most famous algorithm, and so is usually part of any book in algorithms. Okay, so what are now the chapter is about many things, but essentially the reason for binary search trees is a reason of performance, because for all the other structures the performances are not that good as in binary search tree. And again, we use the structure of a tree to do search in a structure, in a data set. Okay, so a binary search tree is, well, it's represented by a binary tree, of course. So there are a couple of examples in the book. One is this one, 6, 5, 2, say 5, and then on the other side we have 7 and 8. And there is also another example. Which is 2, 5, 7, 6, 8, and 5. So again, we are representing data on a tree, but the representation is not exactly that, say, the same as the binary heap, because the structure, as is outlined at the very beginning, is far more, say, complex than that of a binary of a heap. I remind you that a heap is just an array where we think that say, the entries in the array, the elements in the array are organized in a way that reflects the structure of a binary tree, of a complete binary tree, actually. And so we can say something about, we work on the indexes to get, say, some facts about the tree. So we use we force the structure into that of a complete binary tree, and this allows us to work with the indexes of say, of the various elements. So we have keys, and we might have some other data, so numbers in this case, so 2, 5, 7, 6, 8, well, whatever. But we also have, for every node in the tree, we have also 3 pointers. That is 3 sort of variables that tell the node where to find his left child, his right child, and his parent. Okay, I'm referring to this node 5 here. So essentially, do you know what the pointer is? Have you done, I mean, Python doesn't have pointer, I think. What, have you done some C? Yeah, so well, in C is quite obvious because you can use pointers explicitly as a type, as a variable type. And so the idea is that together with any node, you include 3 pointers, 1 to the left child, 1 to the right child, and 1 to the parent of the node. And whenever one of these pointers points to nothing, well, you just say the pointer is null or nothing or whatever. And this means that, say, for every node, we have more than, you see this, you see that you have more than, every node contains more information than the one in the heap. The one in the heap just uses the index of the array. So what is the property of that defines binary search tree? Well, the property is the one that is outlined, is the binary search tree property. Oops. So if X is a node in the binary search tree, then and Y is in X dot right. X dot left. Then Y key is less than or equal X key. And if X is Y is in X right, then Y key is greater than or equal X key. Yeah. The subtree. Okay, so X left is the whole subtree. Yeah, is the whole subtree pointed by X left. Yes. And Y is a node in that subtree, exactly. The keys are bigger. So the idea is that, as you see here, you take 6, and the right subtree is this one, and every element in the right subtree is greater than or equal to 6. And in the left tree, the left subtree, you see that you have 5, 5, and 2, and all of them are less than 6. You can allow for equal members. This is not that difficult, but actually, usually binary search trees are used with different keys, so distinct keys. So the problem, of course, there might be some issues when dealing with duplicates in a binary search tree, but well, you can fix them if you want. So maybe I should be more clear, is in X left subtree, then, and this is sub 3, then this. So that is the defining property of a binary search tree. And the defining property, as you see, is far more rich than the one that defines the binary heap. With the binary heap, where you had only the reference between, say, the link between a node and a parent, okay? So only the node was bigger than, or depending on the max heap or min heap, was greater than or equal to its two children or something like that. That was the only, say, requirement, the heap property, max heap or min heap. In this case, the property is far more rich because it says something about all the nodes. There is another thing which is rightly pointed out by the book, of course, which is what you see from these two trees is that this tree looks like, say, as the height of this tree is less than the height of this. And of course, you could think of reorganizing, say, things in a tree in a different way. And well, essentially, what we see later on is that most of the algorithms that we are going to use here actually go through the tree, and they start from the top and they go down. So, and they are measured by the height of the tree. And the height of the tree is something that, in this case, you cannot predict, because you might have, say, both are binary search trees, and 1, 2, 3, 4, 5, 6 nodes, 1, 2, 3, 4, 5, 6 nodes. But in this case, the height is twice the height of this. Okay, so this is height 4, and this is height 2. And since you are based with since the algorithm measures its performances using the height, there are good reasons for choosing binary trees like these and not binary trees like these. And in fact, in the book, I think is the next chapter is about building balanced binary trees. So when you build a tree, you look for a tree like this. So you try to keep the height of the tree as small as possible. And this is what is usually said, balanced binary tree, usually called balanced binary trees. This is an unbalanced because it has everything on the right side. Okay, the right subtree contains everything starting from 2. Okay, so this is the main structure and the property of a binary search tree. Now, there are a number of things you can do. Well, we see some algorithms in a while. The main idea is that you want to, well, in many cases, you want to traverse the tree and look at all the elements of the tree. And essentially, there are 3 ways of looking at the tree. One way is to, well, is the one that I think is shown as, yes, is in order. The one that is shown first, which is the in order tree walk. That is, we consider a tree, a binary search tree, and of course, since all the entries, all the nodes in the left subtree are less than the root, and all the nodes in the right subtree are greater than the root, then we can start looking at at what's on the left, and then looking at the root, and then looking at what's on the right. And this is called in order. There are 2 other ways of say, traversing a tree, that is looking at every node of the tree. One is called pre-order, and the other is called post-order. And pre and post refer to the position of the root. So you might have this and this, and then, so the root, and then the left child and the right child. Or left child, run child, and then the root. And these are pre-order and post-order. And these structures, I think they are not mentioned here. No, but they might be useful. They might be useful in some cases. I don't know if you do you know what is the RPN, reverse Polish notation? No, or infix Polish. Well, on your Pocket calculator, have you ever used the NH? Well, no, not now. I mean, not anymore now. In the old days, there were pocket calculators from HP that use the reverse Polish notation. The reverse Polish notation is actually a notation that uses a stack, so a structure that, say, puts elements on top of one another. And the idea is that, well, with say, a normal pocket calculator, what you do is type 3 and then type plus and then type 4 and then you press equal and then you get 7. On an HP computer, say in the old days, you type 3 and then you type 4 and then you type plus, and this actually produced. So it's like the operation is supposed to work on the previous two entries, and so if you think of the two entries as two nodes here, and this is the operation, you are actually performing what is called the post-order entry. And the advantage of this is that, of using this notation, is that you don't use anymore the equal sign, so you save one key. And what is more interesting is that, well, with most, say, with all pocket calculators, you use parentheses. And actually, parentheses in this case are actually useless, mostly useless, because you type things in a slightly different way. Of course, you have to get used to this way of typing, and then you avoid almost totally parentheses. And again, this is you start with the two operands and then you type the operation. And this is an example of, say, traversing a tree using, in this case, post order. Well, sorry about that. I mean, we and they were advertising this as a very efficient way of course it was cheaper, and well, it was cheaper for them to produce because is much more, say, of course it's much easier to build a structure like a stack. I mean, you just put all the entries into a say, piece of memory. Memory is organized in part in say, stacks, and so is quite easy. But then at the end, I mean, this proved to be definitely not so popular, and so I don't think that HP is still making pocket calculators, but at that time, 1980s, 1970s, that was the rule. Okay, so let's see how we can traverse a tree. So this is, well, of course, the idea is that we want to traverse a tree and see all the entries. The function that is outlined in the notes is in order. It's called in order tree walk. And takes a node X as input. And the procedure is, if X is not nil, then, well, you recursively call in order tree walk X dot left. And then, for example, you print X dot key, and then you call in order tree walk x dot right. So this is an example of a procedure that goes and traverses the tree in order. So you start by looking at the node. If the node is not empty, because at every step you are supposed to look at a node. Node might be empty if its parent has no left child or right child, or no child at all. And so essentially what you do is two recursive calls, one on the left and the other one on the right. And for every recursive call, you print the key. So for example, in the example above, you print the numbers in order, because you start with 6. So if you follow this, you start with 6. 6 is not nil, so you call in order 3 walk here at 5, and 5 is not nil, so you call in order 3 walk here. And since this is not nil, well, you start with the left child, then you print 2, and then you look at the right child, and it's nil, and so you go back. So the idea is that here, when you call that procedure at 2, x is not so the node is not empty, but then its right child is empty. So the first call in order 3 walk calls for say an empty node, and so does nothing, and then prints the key, and then look at the right node and does nothing, and so get back here. And then you have 5. You already called the left. You now call the right, and so you start again for the right here. You get 5, and the same as for 2. You call the right child. The left child is empty. The right child is, sorry, the left child. Then you print 5, and then you call the right child, and is empty. And then you go back, and now sorry, you print first this one, and then you print then this one, and then you print 6, because you are done with the left sub-tree of 6. Then you print x, and then you go down this way, and then you print 7 and 8. Okay, so this is how the in order tree walk works. It's quite easy to get it. Is a recursive call. The time required for this is, well, you have to inspect, well, you have to print all the nodes, so it's theta of n. Okay. I think there is also a proof. The proof is done using direct substitution and verification using induction property. Okay, you can see it, the proof, but it's not that difficult. Well, let's see how we search a binary search tree. Uh, 289. $290, yes. Binary search trees are heavily used for search. Many structure in say professional database systems and database systems management system are built using binary trees behind the scenes. Because when you look for a key, when, I don't know, say, I don't know how Bocconi database is organized, but when you have a large database and you're looking for, say, something which is, say, one record in a large database, well, instead of having searching through the whole database, you search through a smaller file, which is the file of the keys. And the file of the keys is usually arranged into a binary search tree. So you get immediately the position of the record you are looking for into, say, in the database, and then you point to the database. So the idea is that when you organize files in this way, you keep the database, which is a large file containing all the data, and then you have other auxiliary files, and every auxiliary file corresponds to an index. So essentially is a, well, could be, this is not, of course, the only solution, but could be a binary search tree stored in some way in a thing. And then you look for the binary search tree using, say, the procedure that I'm going to tell you, which is very fast. And then from that, you get a pointer to the record in the database, which is a large one. So you get immediately access to that record. So that is the way it works. And performances are, so this is essentially the advantage of having a database. You split the two things. You collect the data into one place, and you keep the indexes in other places. So, and this is the reason why database management systems usually ask for which index you want to work on, okay? So you can do, say, free text, sort of. Well, usually, I mean, databases are say, compressed data, not, say, uncompressed data. But, of course, this is a completely different thing. So if you know in advance that you are going to look for, say, students at Bocconi by their ID number, matricola, or their, say, last name or their first name, or some other things, then, of course, you keep some indexes, say, updated, so that you can immediately get the answers. Okay, so so this is searching, and so we define the procedure tree search. And the procedure tree search, well, has two parameters, a node X and a key K, and it works in this way. If X equals nil, or key K equals X key, then simply return X. The meaning of this starting statement is that if essentially the procedure goes through the tree by using the structure of the tree, so the property, the binary search tree property, and it might be that it reaches the end without finding the element. So in that case, it points to a node which is nil. And in that case, X is nil. And if you want to return, say, the user, the information that you didn't find, the node, you just return X, which is returning nil, and then you are returning, say, nothing, okay? Otherwise, sorry, this is an equal. Otherwise, you are still returning X. In the other case, which is the positive case, you found the key equal to K, and so you are returning the node corresponding to the key. So you're saying, well, the key you are looking for is here, and then you're returning the node. Okay? So this is the end of and then, of course, if you're not at the end, well, you do the comparison. If X is less than key, sorry, if k is less than x key, then again you return 3 search x dot left k. Otherwise, you return 3 search x right k. So if, well, this is obvious given the binary search tree property. If x is less than the key at the node where you are, you have to take the left subchild and look into the left subtree. Because you already know that the key is there. And instead, on the other case, you look into the other node. Okay? And the case equal. As I said, I mean, the assumption here, the hidden assumption is that we don't have, say, equal keys along the tree. So there are no duplicates in the tree. So, and well, again, it goes down, and say, following the two, say, whatever the subtree is, and then at some point you'll find, or you not find, you don't find the number you are looking for. Okay, this can be done also without recursion, and I think the book says so. So the idea is that, well, yes, it's kind of obvious. I mean, the book makes an example. Probably we will use that example later on. There is another way to write this, which is it doesn't use recursion. And so just mentioning this because might be, so while x is not nil and k is not, oops, sorry, you can't see this. Sorry? This is okay, yes, but no, this is the mouse, it's not the eraser. Say, and yes, k is not xk. So if k is less than x key, then x equals x left. Otherwise, x equals x right. And then return x. So the while loop enters, again, the entry condition for the while loop is that x is not nil and the key is not x key, which is exactly, precisely the negation of this, okay? A or B negates to not A and not B, okay? And then we move, but essentially what we do is we change, so again, the structure, this is the big difference between the binary heap and the binary search tree. In the binary search tree, the node is a structure, is a complex structure, contains the key and 3 pointers. And so you are saying this structure is not anymore x, is x left. And so this is actually sort of doing the recursion in a sense, because you are moving the pointer to the other, you're moving to another structure. And then in the end, you go back to the starting position. And if say if you are at the end of the tree, maybe, I don't know, say x left is nil, in which case you return, and you return nil, or you go down and again, and then at some point, you return x, either with nil or where the key equals that, okay? So these are the two versions of the binary, the querying along the tree. And I don't know if it mentions the thing here, but yes. You know that in the search for an item, what we are doing is actually going down from node X to its children, and then the children of its children, say its grandchildren, and so on and so on. So the idea is that every step of the recursion, or every step in the while loop here, is actually a move down in the height of the tree. So that's the reason why the complexity of these operations are, say, big O of h. H is the height. So essentially, say, required time, which is log n, in terms of the number of nodes. Well, in this case, you don't explicitly say log n, because you don't know how the tree is built, okay? So for a complete binary tree, it would be exactly log n. But you don't know whether the binary search tree is balanced or not. But as I said, usually you try to keep the binary search tree, as you work with the binary search tree, balanced, so that big O of the height, so big O of h, is kind of big O of log n, which is true for complete binary trees, but not necessarily true for binary search trees. Okay, it depends on the structure. We are done. 10 to 1, am I correct? Yeah. Yes, so we started at 10:20, yeah. Okay, no, just for the break too. Okay, there are two other things which are quite easy, but nevertheless interesting. Yes, I think I copied this tree from the book. So it's 15, 6, and 18. And then 17, 20, 3, 7, 13, and 9, 2, and 4. So this is an example of, yes, please. The other one is nil. Every point, when you initialize the structure, when you create a node, you give the node, well, you typically give the parent is supposedly, unless you are starting from the root. Well, if you start from the root, everything is nil. No parent, no children. And the key is whatever it is. And if you are creating a children, well, you give, say, the parent, say, pointer, the value of its parent, and then you leave the children as nil. Say that.
Like in the case of 13, we define 9 as x left.
Yeah.
9 as x right.
Exactly. Yeah. 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 Well, this is usually, yes, it works. Well, every structure that uses pointer, say, follows this convention. Of course, you could use anything that, say, says there is nothing there. And yes. Well, probably for pointers, the idea of having a null pointer is, well, a null pointer is something which is meaningless because at least in C, where, say, originally pointers refer to memory locations, there is no zero memory location. I mean, yeah, it's like, for example, something like that, yes, yes. But since you have this data type, which is usually nil or none in Python or something like that, I mean, so you use that that data type to signal that there is something there. There is nothing there, actually. That is the idea. What if K? Well, in that case, well, you can see both ways. Of course, this is never true. K is not in the tree. But at some point, this must be true as well. Because you go down in the tree, and you go down, say, on the right side of the tree. So say that, for example, you are looking for, what is missing here? 5, say. Okay? So 5 is less than 15, so you move here. 5 is less than 6, so you move here. 5 is greater than 3, so you move here. 5 is greater than 4, so you should move to the right of 4. But then you look to the pointer of the right of 4, and the pointer to the right of 4 is the right child of 4, which is nil. And then you return nil, which is a way to return, say, I didn't find in the 5. That is the working of the thing. Yeah, yes. Because this is a search. So the answer is in terms of, did you find it? So, and the answer is either no, I didn't find it, which is nil, or yes, I found it, and I'm returning the node. Now this is typical of all the pointer structures. Like have you done linked lists? But well, there is another structure. Let me just introduce you to this, because this is very common. There is another structure which is called linked list. Okay, so the idea is that you have, say, a key and a pointer. And the pointer points to another node. So it is a list, but it's a list where each element knows which is its successor. Okay, so the list points here, and then you have another, say, this is A1, this is A2, and also you have a pointer that points to the other one, and this points to another element like this. So say A3, and this points to another element, A4. And then at some point, the list, well, the engineers use this. Well, for us, I mean, this is for engineers. I mean, nil, okay? And a linked list is well, linked because it's linked. That is, every node knows where to go. And this is the basic structure. There are also lists where every node knows not just where to go, but where it comes from. in which case you have 2 pointers, one that points, say, backwards and the other that points forward. And every in structures like this, you typically signal the end of the end of the structure with nil. So typically, for example, in a structure like this, if you want to look for a, so you see the comparison between the two. A binary search tree is very well organized because it knows, say, its parent, child, and is also organized in terms of the relative values of the keys. So you can immediately say whether a number is, say, to the right or in the left subtree or in the right subtree. In this case, usually you don't. Of course, the advantage is in terms of space, because and there is also another big advantage. You don't care about the structure of the list. You just put the elements. And to insert an element here is quite easy. Just remove this and say, take the last one and create another, say, item. And instead of, so make this, so when you created this as a location in memory, so what you do is you set this to nil, and you set the previous one to this. And so you create another thing. And you can also manage easily the insertion of an element. Say that these elements are in order. What if you need to insert an element here? Well, you just, well, there are some technicalities here, but what you do is you create another element, say A34, this is A3.5. You link this to this, and then you link this to this. And well, it's just a matter of, say, not messing up with the pointers, but it's something which is widely used. For example, this is a structure that is used in for storing sparse matrices. Sparse matrices are matrices where, large matrices where the data, non-zero data, are just few entries in the matrix. So in that case, you don't want to waste the space of, say, I don't know, n times n memory locations. So probably a structure like this is much better. It's a list of something which just contains all the, say, the entries that are non-zero. And for each of them, you don't just store the, say, the number, but of course the location, because you need where the number in the matrix actually is. So you say, this is entry, I don't know, this is A2010, this is A2111, and so on, and just few entries here. And then if you want to look for, you know that if you don't find it here, it will be zero. That is the idea. So it's a huge, say, saving of time and space. So, but you see the difference between a linked list or any other, say, trees managed this way and the binary search tree is in the property defining. The property is both its strength on one side, because then when you query the binary search tree, you get the answer because you know the data are already organized. But of course, the drawback of this is that you have to keep the data, say, in the right place. Is more or less what we did with the binary heap. Okay. So there are, as I said, two, say, easy procedures we can call, and one is tree maximum. Given a node X, and so we simply go down in the tree. Sorry, this is tree maximum, so it should be X right. So while X right is not nil, X equals X right. and then we return x. Which is, say, a very concise way to say go down continuously on the right until you reach the end. Reminds me of it's from Alice in Wonderland, I think. Then I think that the king instructs Alice to say, well, you go on until you find the end and then stop. It's kind of. So yes, you continuously go right, and then in the end, when you are stuck, which means that you reached the nil pointer, it means that you are at the maximum. So you are returning this node, because it means that the right node is empty. And of course, the same is true for the minimum. X, which is while x left is not nil, then x equals x left. Return x. What are the guys saying? So right is considered maximum and left minimum. It's not that it's considered. This is just the convention, the definition of the binary tree, binary search tree. Sorry. So the property defining the binary search tree is that every node in the left subtree is less than the node itself. So every number here must be less than 15. Every number to the right of 15 must be greater than 15. That is the property defining the binary search tree. So yes, it's a convention, but yes, please.
Sorry, if we had write some 2 to 13 of, let's say, 21, it wouldn't violate any rule of the binary tree rule because it's in the left tree of 15.
Okay, I didn't get the question. I didn't get the answer, but well, that's okay. I mean, where should 21 be? Sorry. Okay. Okay, that's good. Perfect. Then. Yes, please, Dennis.
I have a question. If we make the tree search more efficient, if we start in the middle in a balanced tree, and then we look where it is, it's like the ordered list. When you start in the middle and see if the right part is larger than the left part, goes to the left.
You're talking a binary search tree?
Yes. Like.
But this is the property is true for every node. So all the say even, well, of course it's true for 15, but it's also true for 6. Every node which is greater than 6 is of course below is to the right of 6, and every node which is, so all its descendants are on the right that are greater than, and the descendants that are less than are on the left. Is this what you were asking? So that is the property is true for every node, not just for the root. Okay. Okay. So now the next, we have time. Would you like to stop now, or I don't know? Well, let's see the next. The next function. The next function is finding for the successor or the predecessor of a number in the order. Okay. So, and this is something that it's, say, peculiar of binary search trees. 287, 291. 292. Yeah. Of course, we assume that the keys are distinct. So, for example, the successor of 13, well, we see here, of course, we see everything here. The successor of 13 is 15. Successor means, think of you put all the nodes in order, okay? And how to get from 13 to 15? So this is the procedure tree successor. X. So if X right is not null, then we return 3 minimum of X right. So, well, this is the first case where the node has a right child. If the node has a right child, there are we can find the elements that are say greater than the node. Okay. So for 7, 13, and 9, and it means that these elements are the closest because of the property of the binary tree, binary search tree. So essentially, we know there is something on the right. So we know that there are numbers, descendants of the node, that are greater than the number itself. Since we want to find the successor will be the minimum of all the numbers that are to the right. The successor is the next one in the order, and the next ones are collected into the right subtree.
Just apply in order to equal get the next they store the result in order to equal in an array and get the next node after the.
In theory, we can, but in practice, this is much more time consuming. Because in order tree walks through, say, the whole list. So it's order of n. In this case, 3 minimum is order of, well, you see it there, is order of, you are going down. So it's order of h. Yes, of course. But this saves time. So, well, we see what happens in this case. If x right is nil, which is the other case, well, we set y equal to the parent of x. Because what we are doing essentially is moving upwards because the property, the key property is this one, is the one that is actually, it says it is an exercise. So if the right subtree is empty, then you have to go up until you find is the lowest successor of x, whose left child is a successor of x, is also an ancestor of x. So you go up until you find 15. That is the idea. So we start by considering the parent, which is in this case is 7, and then while x is, sorry, y is not nil, that is, we have not reached the root, and x equals y dot right, then x equals y, and y equals yp, the parent of y. And then we return y. So this is the case for the other, just to explain. This is the case for the other. So we moved, and now we are, say we are here. So y is now the parent of 13, which is 7. This is a node, and x is actually the right child of y. Exactly the case. So we then move up, and so we set x equal to y. So now x is this. So before we were x was this and y is this, and now x is this and y is this. And again, this is true because y is the parent of y. So is 6. And this is true because y is not nil, and x, now 7, is the right child of 6. And so we go up again, and so, well, change color. This is x, and this is y now. And now, this is not anymore true because this is true, but this is not. You are not on the right. This is the left. Moving to the right means that you are increasing, essentially, because the tree is kind of ordered from left to right. Probably this is the reason why. I mean, because we write from left to right. So that's the reason why they put the say the lower numbers on the and the higher numbers on the left, on the right. Okay. So and it is exactly the fact that you are moving to the right that tells you that you are at the end. So this is the next. And since you have gone up by keeping the right, you know that you are getting smaller numbers, and then you get a number which is greater than. And of course, that number must be necessarily the successor of x. And this is what the procedure does. Well, you had another number here, but that number must be greater than 13 because it's 13 is in the left subtree of this number. So you need at least 14. Well, thinking just of integers, okay? So you might have 14, it would be the same. The point is that at some point you move to the right, and moving to the right, well, this is not so obvious because, I mean, looks obvious, but I mean, there is an exercise there, so it says it requires some kind of careful proof. But the idea is that moving to the right increases, and since you kept everything to the, sorry, yes, moving to the right, you kept everything moving to the left. So because if the children if the child is a right child, it means that you are moving, you are getting smaller numbers. Yes, you're moving leftwards. That is the idea. And you see that what the algorithm does is going up and then stop at some point. So again, it works with using the height of the tree. Who's speaking? Yeah. No. If the successor is? Yeah. It can't be. Yes. Yes. Yeah, essentially you go up because, well, because of the numbers here. Okay. So it's 11:30. Shall we stop now? Say. So we'll be back at, say, 1:45 to noon. Okay. guys cannot hear me. I said that yesterday I found this data structure visualization website. I will share the link with you. So let me share the screen now. So you guys online, can you see the screen now? Thank you. Okay, so this is the website. Kind of. So it contains a number of, say, well, many algorithms. And for example, there is binary search tree, and you can just input insert numbers. So like, I don't know, say 5, and then you insert the number, and then it creates the node, and then you add, say, 12, and thus say 16, and then say we insert 3, which obviously goes to the left, and then 10, no, it was 19, sorry, I said 10, no, not 1, okay, but 10, I told you, 10, okay, kind of like this, okay, and you can play, and the interesting thing is that you can insert and delete, not just insert, but also delete and find the number, and it shows with animation how you go down into a binary search tree. And not just binary search trees. I mean, there are a number of, say, examples here. Okay, so this was just a. Okay, so let's go back to the the final thing I want to tell you, which is about share camera. Okay, which is about inserting an element into a binary search tree. Well, the next chapter in the book is about insertion and deletion of an entry of a node in the binary search tree. Deletion is a bit tricky, and well, actually, you can see it in the book. So essentially, deletion is easy when there are no children, because of course you just remove the node. It's not that easy when there are children, because you have to move the subtrees from one node to another one. So that's the reason why say the algorithm suggests an auxiliary procedure, which is called a transplant, which is kind of doing some surgery on the tree and actually moves the subtree into another place. But as I said, it's a bit tricky. The book says it is tricky, while insertion is, in a sense, much easier. And so I copied this example from the book. And the idea is that we want to insert number 13 here. And of course, the idea when you want to insert a node is to find its place, starting from the root, going down, and finding where the node must be inserted. So you start with 13, you compare with the root node, which is 12, and you know that 13 must be to the right of 12. So you go down to the next node. You start from here, you go down on the right to 18. And then 18 is greater than 13. So at each step, you compare the number you want to insert into the binary search tree with the number that is in the node. 18 is greater than 13, so you have to move to the left. And so you move to the left, and the left child of 18 is 15. And so then you compare again 13 with 15, and 13 is less than 15, so it must be on the left. It must be on the left subtree of 15. Now 15 has no left child, and so you put this and you put 13 here, and you have inserted 13 in the right place. So that is an example of how it goes. So let's have a look at the, say, the algorithm. So the procedure is called tree insert. Takes a tree and a node Z. Now the idea is that Z, so you can't insert a number. What you insert is a node. So this is clarified at the beginning in the say the beginning of the description, before the description of the algorithm. Z must be a node, not a number. So actually Z is a value, the key, and say its left child and its right child, which are both set to nil. So we have a node here. So we know, so let's write it explicitly. Z is a node. And the procedure goes in this way. So says Y is nil. And X is the root of T. So the idea is that you go down, but then at some point you'll end up into nothing, because you need, say, a null. You need either a left child or a right child to put the new node. And at that point, you will be pointing to the that non-existent node. And so you need to keep track of what the parent of the node. So you start with this structure, which is actually, you could think of the root of the node, the root of the tree, and its parent. And you know that the root is the only node that has no parent. Okay? So essentially, Y keeps track of the parent. So and goes like this, while X is not nil, we set Y equals to X. So we move down one level, and then we compare if Z key is less than X key, then X equals X left. Otherwise, X equals X right. And after you get out of this, you set the parent of Z equal to Y. And now, if Y is nil, then it means that the root was, well, the tree was empty, and so the root is set to Z. Otherwise, let's go here. No, maybe I should write this here. If T root, sorry, if Y equals nil, then t root equals z. Otherwise, if z key is less than y key, then y left equals z. Z key is less than y key, yes. Else, y right equals z. X equals nil. Yeah. So you are keeping 2 pointers. One is the x, and the other one is the y, and the 2 pointers are going down together, and y is always the parent of x, and you are going down. So y is above, and x goes down. So you start from the root, and well, of course, you might say that the root is empty, and so you get immediately here. But apart from this case, which deals with an empty, well, with structures that say use pointers, you always have to look about say null pointers at the beginning, because sometimes the object is just a pointer to nothing. Okay. So, for example, as I told you before, with the lists, what you typically have is that you start the list and you say the list is this item, and this item points to nothing because it's just the empty list. So the empty list is a pointer to nothing, and then so it is a variable because it is a pointer, but it points to nothing. And so the first thing you have to check is this: are we dealing with an empty list or with an empty structure? And this is the first thing you do, and then you go on with the the normal case. Okay, so while x is not nil, which means that the root is there at least, and we go down, setting at the beginning y equals to x, because we know that we are going to change x anyway. So apart from the case where, say, x is the tree is empty, we start from the tree, and now we have y that, say, points to nothing, and x points to the root. Now we're going to change this. And since we are going to change this, we start by saying, well, wherever we are going, either to the left or to the right, well, this will be the next parent. And again, this is another, well say in writing the code about this, another trick, another thing that is usually, I mean, a common mistake, is that you do this after, and you cannot. Why? Because this is the mechanics of pointers. Now the x now is in the right place, and will be, if you move x to either the left child or the right child, then you lose what was the x before. Well, you still have the parent, of course, but in general you don't use it. And for example, in linked list there are no parents at all in general. So you typically have to fix the pointer before modifying the pointer, because otherwise you lose the say the pointers. Okay, so you start with this, and then you compare the keys. If z equal if the key in z is less than the key in x, then you move to the left, because you know that you're moving. You need to move to the left, otherwise it's right. In our example, x is here now, and y is nowhere. And then, well, you set y here, and then this is x now, but y and x for, say, in this, say, at this position, they are equal. But then you compare 13 with, say, the two keys, 5 and 18. Okay? So, sorry, you compare 13 with 12 with x key. And since 13 is greater than 12, so the condition is this one, which is met. And so you change x to this. And now x is this So before was X and Y, then you do the comparison, and then you get X here, and X is removed. Because when you move pointers, you're moving things. And now, and this goes down until, so then you do the same thing. So you stop Y, you move Y here, and then you move X accordingly. And again, 13 is less than 15, so you need to go this way. So you put X here. And then you do another step. So you put Y here. And then what you do is compare 13 with the key, which is 15. And when you do the comparison with 15, you say 15 is less than 13, okay, then I must go to the left. But the pointer of, now X is here. And now you should move here. But you can't move here because actually 13 does not exist. So now X points here. Nothing. And so you are getting out of the loop. And you see why you need Y. Why? You need Y because now X is pointing to nothing. Okay? So you set the parent of Z as Y. So now Y was pointing here in the right place. Now X is here. Well, here is not here because it's nil. It's nowhere. Okay? And so, and then, well, if the key is less than the Y key, then, well, now you have to, again, compare again, because now Y is in the right place. And so you know that you ended up in the right place. In this case, is the left one. Again, right and right. It's a mess here. So you already knew, but graphically, that you were going to the left. But of course, the program does not know where to go. So you fixed Y as the pointer here, and Y is the pointer here. And then you are left with 13. And to know where to go, either to the right or to the left, you do the same comparison. This comparison actually has already been done here. It was the last comparison that you did here. But since you have destroyed X, you cannot use this comparison anymore. So you do it again, and then you place Z in the right place. Okay, and that is the working of insertion. Say tree insert. Is playing with pointers is very interesting. Yeah, the assumption here is that, well, this is actually, when you do binary search, I mean, say in applications, the case of equal, say, duplicates, as they say, is not very common. Binary search trees are used for, say, for indexing very large databases. And usually the keys, this is the reason why, are very large things. So for example, you can index, say, the students at Bocconi with a key which is because there are, say, students with the same name, okay? Well, we have, say, if you, I mean, of course, we have access to the database of all the students at Bocconi, just the names and so if you look for, I don't know, one of the most common, say, last names in Italy, like, I don't know, Monti, for example, one of our president, well, you find a number of, and maybe more than one Mario Monti. But you want to know who, say, our president, who is, and you can find, because we have recorded all the, say, the students at Bocconi since its foundation in 1902. And well, in that case, the index for the database would be probably, I don't know, maybe the last name, the first name, or maybe the ID number, the last name, and the first name all together. So it's, and it's supposed to be a prime, what is in database jargon is called the primary key. A primary key is something that is not shared by any two records in the database. So for example, your ID number is a primary key. okay? But sometimes you want to look not just for the, say, well, of course, if you have the ID number, that's the reason for using the ID number, because it is something unique, the primary key. And but sometimes you look for, say, you don't remember the ID number, you want just the last name, and so you create complex keys. And so the probability of getting duplicates is very, very low, extremely low, in applications, of course. Yeah? Not necessarily. You may be adding, well, yes, of course, at some point, I mean, well, say you are adding, I don't know, well, 16 would be here, but would be here, yes, at the end. No. No. There is a final thing I want to, yes, please. You mean here? Yes. Yeah, of course it doesn't. Yeah, it does not. Well, essentially the idea is that the variables are not just variables. Of course, when you say this, I mean, you can, X and Y are the same. But the idea is that Y is there, not is here, because otherwise, since you are going to move it at some point, so you should say change this to Y. This is your. Well, but let me tell you that actually this is exactly the point in using pointers. So pointers are actually not variables in itself. Well, they are variables, of course, but they are actually arrows, okay? So you are moving a structure, X points to something, and you are renaming the pointer with something else. That is the idea. So essentially, the node you are looking at is X, not Y. That is the idea. Y should be the parent, okay? Yeah, I know that is kind of, well, well, if you say X equals X plus 1, I mean, mathematically is not correct. But that's a problem with notation, because whenever you say X equals X plus 1, you're actually meaning X is defined as X plus 1. No. And you know that there are languages, I mean, in Python, the ambiguity is resolved by the fact that for the equal sign, you need the double equal, okay? In C, it is a mess because you use, actually, this is, well, it is the same, but this is an assignment operation that returns something. But this syntax, which is, I think is that of a number of languages, probably many languages in the 60s, invented in the 60s, were like this. Not sure about that. I haven't used Fortran. Pascal for sure. Pascal language was invented for the purpose of teaching programming. And so, of course, I mean, it started from the very good point. And one of the good points is this one. And in fact, in higher level language, in some other languages, you distinguish between what's on the left and what's on the right. These are called L values. These are called R values. I don't know if you have heard about this. Well, the two sides of an equal sign of an assignment are not the same, of course, because you are taking what's on the right and putting in what's on the left. So the idea is that an object that is here is called an R value. At least this is done in C. And this is called an L value. And they have different roles. So sometimes when you read, of course, you have to go into the details of the language, but they have different things. So, and that is the reason for you to, I mean, to be, so of course, so this writing is not 100% clear. Any writing like this is not 100% clear because it requires this step in abstraction, essentially. Guys, I think I'm done. I didn't want to explain the deletion because it's kind of a very long thing, and it's also very tricky. I mean, essentially the process is more or less like this. You go through a number of steps. There is actually the explanation in the book is quite long. There is one only thing that I want to tell you. What you can, well, I already told you that, but the big thing about binary search trees is that the structure, someone asked me, the structure is not an array rearranged or thought as a tree. Is a tree by itself. So there is no array, there are no arrays here, okay? So that is the idea. And that is the reason why binary search trees are more powerful than binary heaps. Another reason, sort of mathematical reason, is that if you look at the properties, which are called technically the invariants because these are properties that are maintained at every time in the structure. A binary heap has a very weak property. It just says that every node must be greater than or less than, say, is its parent. Okay, that is the definition of a binary heap. And this is kind of much less than what you ask in a binary search tree. But the condition is on the subtree, on the left subtree and on the right subtree. So the more you ask in the condition, the more detailed, the richer the invariant is, the more you get out of the structure, of course, because the structure contains more information, and of course, it tells you more, is able to tell you more. That is the idea. So again, is always a trade-off between what you pay on one side and what you get on the other side. That is the idea. That's it. I mean, if you have no other questions, I mean, I'm done with some, say 30 minutes before the supposed end. So if that is okay, that were the topics. Someone asked about, say, having the code for this. I don't know, because we have rearranged the order of the lecture at a later time. But I guess Professor Baldassi is going to tell you something about these two structures in this last lecture. I understand the other one is the mock exam. By the way, how many of you are going to take the exam in presence on, say, December the 10th? A number. And how many of you are going to take the exam in presence in the next? I see. Ah, yeah, because you don't have. This is not a final. This is just a general exam. So you can take it in all the, say, whichever the session. I mean, I see. Okay, I see. I didn't know. Sorry, I forgot about it. Okay, guys.